So the other thing I want to talk about today is transforming your data. Sometimes you look at your data with EDA, right? Exploratory data analysis, which I really encourage, and you see what looks like a difference. I mean, it's clear when you look at a graph. These groups are different from each other. You see that. It's obvious. And then you do your ANOVA and you literally get nothing. Uh-oh. And if we get nothing, that means none of the groups are different. We can't reject HO, and then we never publish our thesis. We never publish our paper, and then we never get we don't get tenure, and we have to find a job. That's not quite. Maybe you violated an assumption. The other day, when I was talking about ANOVA, remember I said that, what if you got an F less than 1? And it's like, well, you shouldn't ever get an F less than 1, but you can because you violated an assumption. Because the assumptions say that you can't get an F less than 1. Like the math behind the F test says you can't get an F less than 1, but it assumes a couple of things. And one of the things it assumes, one of the ones we can fix with the transformation, is the homogeneity of variance assumption. It's probably the case. It isn't necessarily the case, but it's probably the case that when you see a difference but you don't detect it with your statistical test, that the variances are so different that you violate the homogeneity of variance assumption. That's usually what the problem is. And I can think back to an example of one of my honor students, back in 2008, Shauna Barrett, who's now Dr. Shauna Barrett. And Shauna, her thesis was on swearing, which makes complete sense if you've ever met Shauna. She literally greets me with, or signs all emails that she sends to me with, and by the way, I fucking hate you. Which is even fine. We're good friends. But, at least I think we are. Maybe she actually hates me. But, we looked at the data and it's like, oh, this is great, we found something. And she's like, this is great. Except there was, she like 8 F-bombs in that sentence when she said it. And then she went and did the analysis and she came back and she said it didn't fucking work. And I said, oh, of course. It's probably the violation, we probably violated an assumption. I bet we can transform these and we'll fix them. And we did, and everything was fine. So it does happen. You like that transition? Pretty nice, right? So what can you do? You can transform your data. Basically what you're doing is, through some mathematical operation, you are changing the numbers. And I don't. Well, if I teach intro, I do sometimes. If the average is too low on an intro test, I update the marks. That's a transformation. People who, at first blush, you say, that doesn't seem fair. You can just change your numbers. So I'm not changing them arbitrarily. Right? I'm not changing them arbitrarily. I'm changing them all the same way. So my answer to this is it is so. Like, let's say I took all the scores that I had and I multiplied them all times 9/5 and added 32. Do you know what I'm doing if I do that? Yeah, what?
You're changing from Celsius to
Celsius to Fahrenheit. That's all I'm doing. Good man. So if you ever really want to know what the temperature is when you're in the States, if you want to know it in freedom-loving degrees instead of warmongering lackeys of the capitalist degrees. Sometimes I can talk like I'm from North Korea. Multiply it times 5/9 and subtract 32. That's all you're doing. Inches to, you guys did this, remember, for the first assignment, inches to centimeters. It's like, well, that doesn't seem right. Well, it's the same thing. Okay, so you're just changing the units you're measuring with. That's all you're doing. So, the first one you can do is called the log transformation. the first one I'll talk about, so the first one you do. You don't just try all of them. Just keep doing random mathematical things to it until we get a significant effect. Don't do that, right? So, taking a logarithm of a number pulls down big ones much more than it pulls down small ones. Do you remember logarithms? Remember hearing about logarithms at school? No, they don't teach you anything anymore. Okay. So if you did like that number there, so the logarithm of 10,000 is 4. Logarithm of 1 is 0. Logarithm of 100 is 2. What, you see what that's doing? Do you remember this? Remember doing this? Right, it's the power, this is log base 10. So I'm taking what power, 10 to the what power equals that number. Right, so 10 to the 4th gives you 10,000. 10 to the 0 gives you 1. Yes, a 0 exponent gives you a 1. Dude. Something you probably learned in high school math and went, why? And your teacher probably said, that's just how it works. And that's about all I know about how it works, right? 10 squared equals 200. Or sorry, 10 squared equals 200. 10 squared equals 100. But you see it's taking 10,000 down to 4, and it's taking 100 down to 2, and it takes 1 down to 0. Now, we don't usually use base 10 logs. I'm just doing this to show you. So if you, on your calculator, it might say log. The one you're actually looking for through to do this is this. Ln. The natural logarithm. And that's the logarithm with the base e. Remember E showed up early on in the course? Not ecstasy. I'm sure some of you were on ecstasy during the class. I saw some interesting looks in your face. Some of you had glow sticks. Soothers? No? There weren't internet. It's not that fun school. Yeah, that'd be a great school. People are literally on ecstasy during stats class. That'd be. And there's horrible Euro trash dance music in the background. Everybody fails the course, but they love everybody, so it's great. They bring people overdose. But so there's a dark side. I'm saying there'd be a dark side. This is called padding. These are short talks today. But E is the natural logarithm. It's basic natural logarithm. It's 2.7182818. It's a constant in math. It's like pi. Okay? So usually we do that, and a lot of things in nature, that's why it's called the natural logarithm. Logarithmic functions in nature tend to be base E. So you would do the base E, not the base 10 log. So reaction time. If you get an exponential curve, it's the opposite of an exponential, right? So if you got a curve that does this, well, that's turned into a straight line by log transformation. Oh, you can't take a logarithm of a negative number. Your calculator will just look at you and it'll give you that error thing, because you can't. So it's like, what if I have negative numbers? What's the lowest negative number you have? 5. Okay, add 6 to all of them first. Then take the log. Nothing wrong with that. You just can't have negative numbers. You can't take logs of negative numbers. So that would be log of x plus k. K is just a constant. So that's one transformation you can do. It's really easy. And again, with SPSS, if you're doing this, you created a variable, and you just define the variable saying, take all these and take the natural logarithm of those, and it just shows up in the next column. Easy.
Can you just say what you said about the curve again?
Oh, if it's an exponential curve, like going up like that?
Yeah.
One of the things you always want to do is make effort, because then you're going to get a whole bunch of variance. Think about this. If we've got an exponential curve, looks like that, there's not going to be much variance around here, because they're all right around 0, right? But as the number gets bigger, the variance is going to get bigger.
Right.
But when the numbers are getting so much, you're going to get really, like, the variance here might be down to there. You don't want that. But down here, it's just really small. Want to pull this down a whole lot, just do a logarithm. I did that actually on the wall because I had done that in 1997, and they've erased it. So it's back. The funny thing was, I left here in 1998, and I came back here in 2004. And I walked into the room and I looked at it, that's still there. So we fixed it. Doesn't hurt anything, right? I'm a vandal. I'm like Banksy, really, when you think about it. Got a new D, I don't want to get in any trouble. Okay. Square roots. I'm not explaining square roots to anybody. I draw the line at square roots. You should know what those are. Okay. With counted data, and this is what Shauna's stuff was, for some reason, and I'm not going to go into why. Let's not worry about it. With counted data, you end up, so counting just means how many times did this happen? And Shauna's stuff was how many times did people notice there was swearing? Okay, so how many F-bombs did people notice in what they were supposedly listening to that was in another room? It's a neat experiment. And if the means are, and this, one of the things that happens off of counted data is the means of the groups are proportional to the variances. So if the mean doubles, the variance doubles. If the one mean is 3 times bigger than the other, the variance will be 3 times bigger. You don't want that. So you take the square root of the original number. Actually, you might add a constant first because you don't want to use imaginary numbers. You don't want to have negative numbers. So let's say you've got some negative numbers, or you've got some very small numbers. You might add a constant first. You're not going to get negative numbers with counted data. That's impossible. But you might get negative numbers and you have still the means proportional to the variances. Okay, got a constant. So that's another one. There's the reciprocal transformation. The reciprocal is just flipping it over, right? So the reciprocal of 2 is a half. This makes the range smaller because you're taking a whole bunch of whole numbers, perhaps, and turning them all into fractions. They're all now between 0 and 1. And if that excuse me. Yeah. So the variance is going to be smaller if the range is smaller, right? This is good with latencies. So you've got a latency. How long does it take to finish a task? Okay. And that's not an uncommon type of measure. In fact, my honor student, Samantha, who I was talking to today, is going to be doing stuff with, well, hers is also reaction time, so we might end up log transforming her data, but we might end up using reciprocals. Because all you're doing is changing time into speed, really. Yep. What about arcsine? Oh, trigonometry. And you said there'd be no trigonometry. I did not say that. I specifically said that trigonometry was exceedingly important. I don't think I said that either, but how are we to know? It's not like these lectures are recorded. Oh, wait. They are. Okay, this is with proportions. This is another thing that we had to do to Shauna's data. So you got a proportion or a percent. Same thing. What this does is it stretches out, and because of the way the mathematical function works, don't worry about it, but the way that an arcsine works is it stretches both tails out. And it's like, why would you want to do that? Well, you got proportions. Like, let's say you've got percentage correct, and it's 2 alternatives. What's chance? 50%, right? So what are you going to get most of the time? You're going to get a lot in the big meaty part of the curve in the middle, 50, 60, 40, and very few at 100 or 0. So you're going to get more variance here and less variance at the tails. What I want to do is pull the tails out. And there's a way you can do that, and that's by taking the arc sign of a number. Okay? You actually don't just take the arc sign and take the square root of the number, then you take 2 times the arc sign of the square root. It's called the arc sign transformation, but it's really 2 arc sign times the square root. So this is used very often. You'll see this, in fact, if you guys start to read some of the literature, which I kind of encourage you to start doing because you're going to have to do a literature review next year, or you've maybe done this or you already did one. You've been reading stuff, you may have had proportions, percent correct, things like that, and you'll see that it's transformed. You may not have paid attention to that at the time. Go back and take a look, you'll see it's transformed. So it's 2 arc signs square root. Proportions, percentages, that kind of thing. Okay, questions about these before I wrap this up? So the question you might ask really is, when do you transform your data? And not every chance you get. It's not the case that the first thing you do when you get a bunch of data is say, well, I'm going to do a bunch of arithmetic now. I'm going to take the logarithm and then the arc sign, and then, I don't know, maybe I'll multiply them all times 30. Like, you don't just do that. Frankly, if you find a significant effect and you don't have to transform the data, it's so much easier because explaining to people that you did, explain to the common people, not to us, right? So not us, we understand. But explaining out to the world that you had to actually do a transformation of your data, like let's say you're giving your talk at your honors thesis day, when you give your talk in front of all the people in attendance are there, and there's people from the community, and they always ask crazy questions that don't matter. Then you get a couple from me or some of the faculty, and they're better questions, right? General public asks questions like, well, not in my experience. And you go, okay. It's fun, actually. The thesis day is great. It's coming up in a few weeks, right? End of March. Go to it, see what it's like, support your student colleagues, your friends, but also see that it's not scary to do. You know why it's not scary to do? Because people don't ask good questions. The general public has no clue how this works. But the general public sees that we did 2 times the arc sine square root transformation, and they go, I didn't take trigonometry. You don't want that. And frankly, you know what? A lot of people who have certain levels of sophistication in various scientific disciplines don't have that kind of sophistication. So they'll look and go, why did you do that? So it's easier to explain if you go, yeah, here's the data. It worked. Or here's the data. It didn't work. So you don't just do it as a matter of course. But if the variances are messy, you owe it to yourself to do this. And you pick a transformation based on these sort of rough guidelines I've given you. I've got these from all kinds of different sources, so I can't tell you exactly where it all comes from. But just pick one of these. But if your data don't violate an assumption, you don't transform your data. And the assumption I'm carrying about here is always homogeneity variance. You can't, if you don't have independent events, it doesn't matter what transformation you've done, you can't fix it. And you might say, what's messy? What does messy mean for variance? One is 4 times bigger than another. That's the rule of thumb people use. It works okay. It's not always the case, but if you see one variance is 4 times bigger than another, and in fact, again, going back to Shauna's honors thesis, she had data, there was one group that was like 8 times bigger than another. And I said, well, it's right here. And she said, well, what am I supposed to do? And I said, aren't you my TA in stats? She said, well, you give me a key. So, you got a PhD in neuroscience. Lives in New Zealand. So you don't just do it as a matter of course, hard to explain. By the way, when you present your data in a graph, you don't present transformed data in a graph. Because I don't know what 100% means. I know what 50% means. I know what 0% means. I don't know what 2 times the arc sine square root of 100 is. Like, I just don't know that. I don't have arc sine tables in my head. So you always present the untransformed data in a paper, in a talk, but you talk about how you transform it. You have to mention that. Right? I'll say that a lot of people will think, oh, it's proportions, you have to do that transformation. My PhD supervisor said that a lot of the stuff I was doing was percent correct. And she said, why didn't you transform it? I said, because I don't have to. It worked already. And she said, well, you should transform it. I said, I'm not going to do it. You don't have to. Why should we have? No. And there's like one thing in the world I knew more than she did, it was statistics. Everything else she knew more about than me. And sports. And US politics, probably. There's like 3 things, but that was it. The only professional thing, though, was stats. So she said, oh, I trust you on this. Questions on this stuff? Pretty straightforward. I hope. That's the plan, anyway. All right. And that wraps up our 2 mini lectures for today.